works? Yeah, it works. Awesome. Cool. All right. So, first of all, I would like to thank the organizers for giving me the opportunity to be here. It's my first time in Brazil, so it's quite delightful. And I was even more pleased when I realized that was the same time as the Copa America, but apparently the conference is exactly organized in the gap when there are no games. So, unfortunately, I will be away when they play against Argentina, would have been nice to see. And that would have been turbulent, probably. So let me just give you very briefly a sort of context for my talk. So this is sort of a story that's about 3 years or so in the making. We were drawn to this topic more or less by accident. When we started working on a very simple system, there was a weakly interacting Bose gas in an optical box trap. And then we realized that we could do something interesting about turbulence. And as we moved forward, this is really an ongoing story, and every time we're adding a piece to the jigsaw, we're sort of making a more and more complete picture of a given scenario of turbulence. And by now, we're reasonably close to have a fully understood scenario of turbulence, at least in one case. And we're almost at the stage when we're trying to some sort of clean up some corners. So this story, actually, I started it when I was in Cambridge, and it sort of followed me at Yale, where I am at the moment. So before starting, let me step back just a little bit before starting to explain the specificities of our experiments. So the audience here is an audience that has a strong background on turbulence. So I won't have to introduce any of that, which is pretty convenient. But just as a matter of sort of historical significance, turbulence was understood as the study of complex flows at high velocities. But very often when you present the kind of turbulence topic to a more atomic physics / condensed matter audience, people are sort of scared a little bit by this term that they feel is completely disconnected from what they do. But in fact, these days, there is actually, it actually fits sort of nicely in a broader picture of the study of far-from-equilibrium states of fields. And so at the beginning, I will start with some classification, which is a pretty dangerous exercise when you talk about complicated subject. But I think for pedagogical purposes, it's quite useful, and it definitely helped me. So if we start, sort of an abstract diagram with an arrow of complexity, then there are the initial states, the initial conditions, which are usually fairly trivial states, equilibrium states that we know how to obtain from general thermodynamic principle of maximum entropy. And what we're interested is to find sort of steady states or quasi-steady states that really don't look anything like these equilibrium states. And so there is, broadly speaking, two kind of ways to get there. Experimentally, almost every experiment can be sort of classified in one of these two things. Either you quench your initial state by changing some parameter very quickly, interaction strength or temperature or something like that. And then as the system is no longer in equilibrium, it's going to evolve back to the initial state. But sometimes for given quench parameters, the return to equilibrium is not all that simple. And you can have something that looks like that, so a free evolution, where for a certain amount of time, you actually get into something that looks like well-defined non-equilibrium steady state. And there are lots of very interesting examples of experiments that have been done like that, but the experiment I'm going to show you is one that's conceptually much simpler, which is just to take this equilibrium steady state, equilibrium state, and just continuously force the system. And if you continuously force the system at least hard enough, the system will will leave its equilibrium state and then go into somewhere else and can never go back to equilibrium. And so, very broadly speaking, I think that two of the most interesting questions that arise in the field are actually understanding whether there are some interesting, well-defined far-from-equilibrium steady states, from which you could understand turbulence as being one case, except that steady has to be understood in a fairly loose sense. And the other interesting problem is the question of the emergence of some universal behavior in turbulent dynamics. Because obviously, you want to learn something about the system that is not just specific to the experiment that you're doing. if the state that I obtain is crucially depending on the way that I force my system, and every time I change the forcing I get a completely different result, then it's not going to be very interesting. You have to, yeah. Yeah, so you should call it steady state. I just put it quasi because you'll see that I'm going to talk about something experimentally that we call a steady state, but it doesn't last forever. So it's as close as experimentally can be a steady state, but you'll see that over a long period of time it actually changes. Well, I mean, when I say steady state, I sort of implicitly assume some sort of statistically steady, yes. Yeah. Quasi has more to do with the fact that, you know, you always exploit some sort of separation of scales. It looks steady in a certain period of time, but then if you wait too long, something else happens, which then means that it's not a true steady state. Okay, so this is sort of like a really broad painting on topic of far-from-equilibrium states, and in the context of ultra-cold atoms, from which I'm a part of the community, this has been really a booming activity in the past several years, and this problem has been approached from a variety of different angles. So I'm sort of putting here a mosaic of quite a few experiments that have been done. Some of them, sort of strictly speaking, fall into fairly standard terminology of turbulence, but some of them also quite recently fall more into this far-from-equilibrium dynamics. But it's fairly obvious that there are some links between these experiments. Now, just to add another layer of classification in the story, I'm going to borrow a picture that Carlo introduced because I like it very much. It was shown actually earlier this morning by another speaker, which is the understanding of vortices on different scales. Either you look at one given tree, you look at several trees, or you look at the entire forest. And so just to make the kind of category of my talk more clear, if vortex turbulence look like this, well, it's not really turbulent because it doesn't move, but you get the picture, my talk landscape is going to look something like this. Okay, so as you can see, there are not many trees around, but you actually see these ripples. And so this talk will be really about wave turbulence and not vortex turbulence. Now, some people in the audience might be familiar with one of the two or both of them. I find it useful to summarize the things that they have in common, the things that are different about the two, because it's fairly rare to actually have a talk that talks about both of them. So I think that when you have people from mixed background, it's useful to do that. And you know, as pretty much everyone in the audience know, you know, cascades are these universal transport laws that don't involve any scale, at least in a given window of typically of length scales. The traditional historic example is hydrodynamic turbulence that's driven by vortex stretching, and then this famous image of eddies length scale. But there are also other energy carriers, for instance, sound waves. And so we know that turbulence is actually more than just a chaotic velocity field. And so you can form other type of states, which I'm going to very broadly separate into two categories. And this is sort of a simplification, because very often you try to work on one or the other, but very often there is an important interplay between the two. So separating them strictly is always a little bit dangerous. And so just to fix some ideas, you know, in hydrodynamic turbulence, typically the important observable is some velocity field. The equation of motion can be Navier-Stokes or whatever favorite hydrodynamic equation you like. In the case of wave turbulence, typically the quantity of interest is some amplitude of a wave field. So it can be, in this case, in my talk, I'm going to talk about the momentum distribution of atoms. It can be the height of wave on the surface. And the typical equation of motion is going to be a kinetic equation that couples these different populations. Now, the nonlinearity in hydrodynamics, typically some inertial, some convective term v dot grad v. In the case of waves, it's a direct interaction between the wave. That means that these things actually don't evolve separately. They actually interact and do some non-trivial things. And so, broadly speaking, a turbulent state is a state in which you have a flux that is scale invariant. So, for instance, the most famous example is an energy flux that doesn't depend on the scale, and you have the same thing for wave turbulence, and this flux can be a flux of different quantities, which in general is not going to depend on k. Now, in the case of hydrodynamic turbulence, at least the simplest version, you have the famous Kolmogorov spectrum of incompressible kinetic energy, and more generally in wave turbulence, you have scaling laws k to the minus gamma, where this gamma is a number that can depend, for instance, on the dispersion relation of your wave and the exact wave equation that you're talking about. Now, the dissipation typically in hydrodynamic turbulence has to come from some viscosity, which is going to dissipate the energy ultimately. The question of how quantum turbulence is dissipated is sort of a different story, so I'm not going to get into this coupling of vortices into phonons and things like that. And in the case of waves, it actually sort of depends on the situation that you're interested in. And so one of the ongoing challenges, particularly for experimentalists, is to try to make things as simple as possible. And one way of making it as simple as possible is to actually study one of these two without having the interplay. But as I said before, they are not strictly independent, and the interplay can, in some instances, can be crucial. And one important example is dissipation in quantum turbulence, where you can have a vortex tangle that ultimately transfer the energy into a cascade of Kelvin waves. All right, so this is for a broad introduction. Now let me paint a broad stroke picture of what this story is going to be about. And so by now, after a few walks, we can, I can paint things after the fact as sort of being fairly obvious, but well, it took us a long time to understand those. But right now, we can I can actually structure that in a fairly simple way. So you're taking a certain field, and then you force it on a very large scale, 1/kf, where k is the momentum of the forcing perturbation. And so as you force your system, you're going to create larger and larger harmonic of your field until you're ultimately going to hit some dissipation. And after this dissipation is reached, the system balances between injection and dissipation, and you can create a non-thermal steady state. And so this gives me, I'm going to separate this talk into three broad chapters. One is the story of the energy injection. How do we put energy into our system? And you'll see that it's actually very simple to understand. How do we get to the regime of this turbulent steady state? And then when we're there, what happens? And we have the possibility to actually measure the cascade flux in our system. And the toolkit to do that experimentally, so we put together quite a few things, and I will go over them fairly quickly. So we worked with the uniform density quantum gas. So that was something that we introduced a few years ago. So before, quantum gases were produced in harmonic potentials, which meant that their density was actually inhomogeneous in the trap. When you want to do turbulence, the subject itself is sufficiently complicated, so it's nice to simplify it as much as possible. And definitely, if you want to observe momentum space dynamics, it's nice not to have it coupled to real space. And so in our case, we implemented what's called an optical box potential that allows us to trap the atoms with a quasi-uniform density. We implement a very simple large-scale forcing, and then I'm going to talk about the additional tools, the measurement of the wave occupation spectra, which are the main observable of wave turbulence. How it turns out that our system has implements an interesting tunable dissipation scale, and how this allows us to measure directly the cascade fluxes. Now, for the experimental slide, I'm going to go very quickly on that, just to give you some numbers. So the way that we prepare our optical box, we just shine a beam on the device that's called the spatial light modulator. This beam is blue detuned compared to the transition of the rubidium atom that we use, meaning that these lights are repulsive. And if you create this ring and two sheets and you cross them at 90 degrees, you can create a cylindrical box where the atoms sit in the dark region of this trap. And so here we have a typical absorption image of the atoms in this box potential. And here I give you some typical numbers about the scale of the system. Obviously, for people that are familiar with helium, the numbers are widely different. The numbers are smaller, the temperatures are much smaller. And the ratio of xi over L is typically 1 over 100. Now, one thing that is important is also that the interactions are weak in the sense that the chemical potential is much lower than the temperature, and typically much lower than the critical temperature for BEC, which we will find later is actually going to be very convenient. So now, we spent a few years actually studying the equilibrium property of this gas, which I'm not going to talk about at all. I'm going to move directly to the non-equilibrium part. And so the way we did that was very, very simple. We used a pair of coils to create a magnetic gradient along this axis such that we can actually apply a linear gradient to the atoms, and the magnitude of this gradient can be made to oscillate in time. So the shaking potential looks like a certain perturbation, delta U over the size of the system, the box size. And then we have sine omega t, and x here is the coordinate along the box. So now before I show you what happens when you do that, let me, for those who are not familiar with ultra-cold atoms, how we can typically extract the wave occupation spectra, and this is very convenient for us. We do that by a technique called time of flight. So what we do is, apologies for those who know about that, but it's quite important to fix the notation and also some caveats. So we take our box, and if we want to measure this momentum distribution, we abruptly switch off the trap. The atoms are no longer trapped, and then they are going to expand. They are going to expand in an environment that has been very well, for which gravity has been very well cancelled. I'm not going to talk about that in details, but it's very important that the atoms don't feel any force when they fly. And then after some time, when the gas has expanded, you can shine a laser along a direction I'm going to call Z. This is our imaging laser, and then we're going to look basically at the shadow of the atoms, and then we have a fake color image of the density of the cloud after this time of flight. Now, what is interesting is that I can do under some specific hypothesis, I can do a mapping between the coordinate r and the momentum k that I deduce from this r. I'm just saying that if my flight is ballistic, the position after some time gives me information about the velocity distribution inside the trap. And so once you do this mapping, what we get is just a small subtlety. We don't get the three-dimensional distribution, but we get one that has been integrated once along the direction of the laser. But this essentially gives us direct access to the momentum distribution of the gas. Now, it's important to realize that it's a common technique that's been used for various things, but there are some very important things that you have to be careful when you do that. And this relies to the circumstance under which you are allowed to do such a mapping. And what's very important is that you should have a free flight, so there shouldn't be any residual forces while the atoms are flying, or the atom's flight should not be modified by interactions. And another thing that's not strictly speaking necessary, but it's very convenient, is to make flight that are long enough such that you forget about the memory of the cloud inside the trap. So if the cloud has expanded a lot compared to the initial size, then the initial distribution, spatial distribution, is actually irrelevant. Okay, so now let me go back. Yes. Sure. The fact that it's free, in the sense of no residual force or no interactions? Yeah. Yeah, that's a good question. So one, I'm not sure it's simple, but one way to do that is to be able to measure the momentum distribution by another method. Now, I'm actually going to show a picture that usually, when nobody asks the question, I just pretend that there are momentum distribution, but they're actually not, precisely for those reasons. So I'll come back to that later. But in more interesting situations, for instance, in the turbulent steady state, we actually did implement a different technique to show that the two of them were the same. It's just that this one is actually much faster to take, and the signal to noise is better. But there's no trivial answer. Usually you have to compare that to something else that you know. Yes, so I can relate the color here. So red is most photons absorbed, and blue is least photon absorbed, and I can do a very simple relationship between this and the integral of this quantity. So the simplest way to do that is, okay, let me just use some jargon. So these colors are what's called optical density. The optical density is the log of the intensity of the light that goes through divided by the light that would go through if there were no atoms. And you can relate that directly to the absorption cross-section times the integral of the density here. So what we have is really a spatial distribution. It's not a momentum distribution. The momentum distribution rely on the mapping between the position and momentum. Yes, yes, yes. What we count here is the number of photons that went through, and we compare to how many photons would go through if there were no atoms. And from that, you can extract what's the density of the atoms that went through to a Beer-Lambert's law. Yes, exactly. Exactly. Yeah, yeah. Exactly. So when I look at those, I have to, well, I would like to assume that I don't need to know from which side of the box they came from. So it's just exactly a point source approximation. Okay. So now let's go to the table of content, and now I'm going to move to the first part, the energy injection. So now the energy injection, to understand how we can inject energy into the system, I'm going to go, make a very simple experiment. I take this almost pure Bose-Einstein condensate, going to give it a very small kick of our coil, reestablish the box as it was before, and then just let the system evolve. And so what we realize is that if you do that for a short period of time and you don't do that too strong, then you realize that after time of flight, the center of mass oscillates as a function of time. You see that inside the trap, the center of mass velocity was oscillating back and forth. Now, we studied this in detail, and I'm not going to talk about that too much, but you can quite easily calculate that the frequency of this mode corresponds exactly to the lowest lying mode of our Bose-Einstein condensate, meaning that I have a many-body ground state, and this is exactly the first excited state. There is really nothing below that. And this is predicted very simply by Bogoliubov theory. It's proportional to the speed of sound, which is itself proportional to square root density. So if we change the density in our gas, which we did, we can see that the frequency changes in the way that we expect. Now, let me also mention that this mode is actually not as trivial as it looks, particularly because our gas is in an interesting regime, which is that if I do the same measurement above the critical temperature, so I have no BEC anymore, this mode doesn't exist. And the reason why it doesn't exist is that the mean free path of the particle is about 10 times the system size. So it means that I have basically a completely ideal gas. And so the only thing that can oscillate at this frequency is the Bose-Einstein condensate. And this is a very nice conceptual start for a direct matter wave cascade, because I literally cannot excite the system at any larger scale. This is really the lowest lying excitation of the system. Now, this is nice at first, but when you think about Bogoliubov to lowest order, Bogoliubov tells you what are the eigenmodes of the excitation of your system. But if you want to create a cascade, obviously you need some coupling. These waves have to interact with each other. And you have some interesting picture that arises, which is that usually what you have is that your excitation lies somewhere in the spectrum. And typically, for an infinite system, you would have what's called Belyaev damping, when the phonon could actually break into smaller pieces. In our case, you see that damping can actually not be that trivial, because there is actually nothing to decay to. So you see that anything that would happen to this mode has to be nonlinear. You have to have several of these that have to combine to create a higher excitation. And this is indeed what we observe experimentally in a simple way. So instead of doing this kick experiment, we're doing a modulation spectroscopy. And what we find is that, at least when we do it very quickly, you see that as a function of the excitation frequency, we see indeed a resonance. So if you measure the center of mass velocity as a function of time, this is continuously forced. You see that above and below some resonance, it's quite small. And then when it hits the resonance, then the oscillations are quite larger. But you also see that there is actually a steady state here. And this steady state has to imply that there is some forcing, particularly if it's a steady state with just a single frequency. No, we actually just study one mode. Yeah, it's the smallest K. It's actually the one where the wavelength is twice the box size. Yeah. Exactly, yes, yes. Belayev assumes that you have a continuum of k where the phonon can actually break into 2k. So this is actually already quite an unusual situation. So now what we can do is put all these measurement of resonances as a function of the drive strength. And what we find is that this mode is extremely nonlinear. And here are some traces of these resonances. So these are resonances for various drive strengths. And we see that as we drive it, the resonant frequency doesn't seem to shift almost at all, but the width of this resonance increases enormously with the drive strength. And within our experimental resolution, when the drive strength goes to 0, the line width actually also goes to 0. So it really shows you that in the linear limit, this is indeed an eigenmode of the system, but as soon as you have a non-zero delta U, you have dominant nonlinear effect. And so this really shows you that this mode is actually necessarily coupled to other modes as the drive becomes non-negligible. So now we can look, we're actually currently working on understanding the details exactly of this nonlinear coupling. But now I'm going to switch gears a little bit. How much time do I have? Yeah. Not all that much, I think. Okay, good. So now, for the next part, I'm going to jump directly to the steady state, and the reason why I'm not following the time chronological order, I'm actually following the historical order, is because it's actually easier to understand that way. And so what happens is that when we take this mode and we shake it long enough, hard enough, and I'm not going to get into the detail of what these two words mean, what we find is peculiar in the images in time of flight. So initially when we take this image, we got this sort of diamond shape that's characteristic of the expansion of our BC from the box. When we shake it hard enough, we find that the distribution becomes more and more isotropic, even though any given realization actually looks a little bit messy. If we average over many realizations, we get something whose angular weight becomes flatter and flatter. And I can also convince you that this is not just a thermal state, because if I stop shaking at this point, my BC reappears almost entirely with just a very, very small increase in the thermal fraction around it. So you see that the energy is large compared to the chemical potential of the BC, but much, much smaller than TC. So this is an isotropic state that is really very non-thermal. And here I actually plot in dash the velocity of the particles that would have an average energy of kTc over 3. So you see that even in our turbulent state, most of the atoms have actually a very low energy with respect to Tc. Now, if I take this momentum distribution and put them on a log-log plot, we find something quite striking, which is that as we shake more and more, the weight is transferred from low k to high k. But more importantly, you see that past a given time, the momentum distribution no longer changes. So you see between this orange and red, there is actually quite a long time difference in the shaking, and yet the distribution themselves almost don't change. And so if we put them on the log-log plot, we see that in some intermediate, albeit rather small range, the momentum distribution has a power law character. And so it's easier to be convinced by that it's not just merely a curved momentum distribution by plotting what's called a compensated spectrum, k to the power gamma minus 1. This minus 1 comes just from the fact that this is an integrated distribution. And so from that, we can extract the value of gamma, which in our case is about 3.5. To get that, well, you actually don't need many to get the signal to be so low. I think that here we average something like 30 or 50 images. So it's actually very fast to take. Yeah. Yes, I'm going to talk about that, yes. The question is, yeah, what happens here? Yeah, I'll come to that in a second. So now we have this value of 3.5, and it would be interesting to understand, to have some deeper insight about what is gamma. When we did brute force Gross-Pitayevsky simulation of our system, we actually found a value that seemed to be an excellent agreement with the experiment. So we find also a power law for n of k with the power of 3.5. Now, I don't have a lot of time, so I'm going to go really fast on that, but just as a sort of quick reminder about a very convenient framework to understand this kind of situation. It's called weak wave turbulence, which is a theoretical framework. Some people in the audience actually know it certainly much better than I do, but let me give you a very, very quick summary. So you can, from Gross-Pitayevsky equation, derive what's called a kinetic equation, which has a form of dn by dt is proportional to some collision integral, which I'm not going to write, but it's just something that really looks like a Boltzmann collision integral. And in the inertial range, you can derive from this kinetic equation, continuity equation for particles and energy. So these really look exactly like you would expect for continuity equation, except that this divergence is not a divergence in real space, it's a divergence in momentum space. So you see that this thing already encodes this idea of locality in momentum space for turbulence. And I can write also for weak enough interaction, the energy spectrum being the dispersion relation omega times the momentum distribution. Now, one of the surprising prediction of Gross-Pitayevsky in this case is the existence of two cascade solutions. So it's really analytical solutions that have been found in Gross-Pitayevsky turbulence, which is a direct energy cascade with this k minus 3, and an inverse particle cascade with this minus 7/3. And these, the direct energy cascade has a constant flux and a zero particle flux, and the inverse particle cascade has a zero energy flux and a constant particle flux. Now, for an experimentalist like me, the first time that I saw that, I said, like, what the hell does that even mean, to have a constant flux with no particles? For me, it's obvious that the energy is actually carried by particles, so the particle flux can never be zero while maintaining a constant energy flux. And it turns out that working on the experiment sort of allowed us to demystify the meaning of this mathematics. And the mathematics means like that just because you're already implicitly assuming a limit of zero dissipation scale when you're considering this result. There are some interesting problems about the experimental relevance of these predictions, because weak wave turbulence makes some assumptions that are not necessarily true. And to what extent is it really independent of the forcing and dissipation, but I'm really not going to go into those details. Let me move on to the last experimental part here, which is a simple realization in our system that our box potential actually gives us a synthetic dissipation scale. Now the meaning for atomic physicists is almost trivial, but the consequences are not, which is that the trap has a finite depth, meaning that if the particles have an energy larger than the depth of our laser box, the particles are just going to jump overboard. Meaning that if you have this cylindric potential like that in real space, in momentum space, it actually looks like a sphere whose radius is this momentum cutoff kd. So the forcing would look like an anisotropic forcing here because I shake along one direction, but the dissipation would actually be isotropic. And this gives us also very simple access to a particle flux just by realizing that if we take our number of particles and differentiate that versus time, what we get is directly the particle flux through the sphere of radius kd. So the only thing that we have to count, again, from a continuity equation point of view, it sounds almost trivial. If you want to count the flux of particles that go through there, just count what's inside and see how it evolves with time, and you'll get the flux of what is going through. Now, something important for people who are used to hydrodynamic turbulence, what is very important is that here we actually measure the total energy, not just a hydrodynamic energy, meaning that we have the entire energy of the system. There is no dissipation in the system in a strict sense, because we measure the total energy of the system. There is no some hidden viscosity that will dump energy in some place I actually cannot see. And so the only dissipation in the system has to involve some particle losses. If my box had an infinite trap depth, I would never lose any particles, so I would never dissipate any energy. And one sort of amusing statement is that, understanding that you can actually control this trap depth is sort of a way of seeing that we actually can directly tune the viscosity of our system by changing the trap depth, at least within this analogy. So now let me show you these very simple measurements. Just count the number of atoms as a function of time when we shake the system. We just do some more complicated things just to avoid some systematics. It doesn't really matter. The bottom line is that we measure the atom loss as a function of the shaking time for different trap depths. So these different trap depths means that I have some different effective dissipation. And so what we find is that for a while nothing happens, and then when something starts to happen, then you see that dN by dt is roughly constant. Now it's not only roughly constant, you see that the slope obviously depends on the scale at which I set the dissipation. So now what we can do is extract these slopes for various trap depths, UD. And so what we find is that on the log-log, we have about an order of magnitude in the change of this trap depth. And what we find is that the slope of n is linear quite nicely over this entire range. Now, this is where I'm going to go back just for a second for this quasi-steady state. You see that it's actually not linear all the way. At some point, it actually bends. The reason why it bends is that here the loss are actually so high that the system is really not in steady state anymore. The driving is no longer as efficient, and I'm basically depleting my condensate. So you always have to assume that turbulence occurs for as long as the number of particles in the box remains not that far from the initial number you had. But you see that if you extract the initial slope, you get something that's really nicely linear all the way. And what we find is that we get that the particle flux is very close to being proportional to 1 over the trap depth. And rephrased, the particle flux is very close to 1 over kd square. Now, there is one sort of almost trivial way of interpreting that, but it's actually dangerous to do it, is to say, oh, but if your energy injection rate is constant, then it's obvious that pi n has to be proportional to 1 over ud just as a balance of energy. Now, the reason why this statement is not obvious before the fact is that it's not obvious when you shake the system at a fixed amplitude that the energy input rate actually doesn't depend on ud itself. So you already assume that you know something about the steady state in order to say that, but here we didn't even assume it. We just see that in steady state, if we shake it at a given amplitude, we indeed find something that is 1 over ud. So we also did that, this numerically, and what we find is these points here, which, you know, depending on whether you're an optimistic or pessimistic person, I could say that the agreement is very good or not so good. I would say at least from, you know, semi-quantitative point of view, the agreement is not too bad, specifically when you think that there is not a single free parameter in this problem. So it's really a turbulent situation where everything, absolutely everything is fixed, and so the agreement is actually fairly reasonable in that sense. And now we find one of the demystifying claims, which is that the particle vanishes indeed in the limit of zero dissipation scale. And now the meaning for that is very simple, which is that if I put my dissipation scale to plus infinity, the number of particles that I need to dissipate in order to maintain a constant energy flux actually has to go to 0. So it means that for any real situation, the particle flux is never 0, but it's going to go to 0 as ud is going to go to infinity. And you see that all these sort of pieces come together very nicely because the fact that pi n is proportional to 1 over kd square actually also tells us that this is indeed a direct energy cascade. Now, if I take back my relationship between epsilon and n, well, naively, I would think, okay, I can then write the relationship between the energy flux and the particle flux just by adapting this equation. And this equation is actually completely wrong. It actually cannot be true in steady state because in steady state, you're supposed to have k-independent fluxes, but you see that omega does depend on k. So it means that this equation actually never applies. And the subtlety here is that this equation applies only at the dissipation scale. And from the continuity equation, it's quite simple to show that out. So it means that I can relate the energy flux and the particle flux at the dissipation scale. And indeed, in this scale, we find that pi n, which is 1 over kd square, I multiply that by kd square, I indeed find that while the particle flux go to 0 when ud goes to infinity, the particle flux the energy flux is constant. Now, I know I'm going to upset a little bit Davide about that, but I can't resist. There is an analog. This is actually a funny analog to the Zeroth law of turbulence. I'm very happy to go into a debate about that, but if I put all the words together, the statement still seems to apply, which is that for fixed forcing, the energy input and the dissipation rate tend to a constant when the dissipation goes to 0. And obviously the meaning of all these things is quite different because here dissipation goes to 0 means ud goes to infinity, but still this statement applies to our system, which is, you know, obviously very different from Navier-Stokes turbulence. All right, let me now finish by one last thing, which is how we actually get to the steady state. And to show that, let me just uncover something that we saw before, but I didn't mention that. If you look at the traces, you see that before we get to this constant slope, there is actually a latency period where nothing happens for a while. Actually, this while can even last for up to 2 seconds. And this is very indicative from what you expect from a cascade front. And so if we use sort of the textbook image of a turbulent cascade, when you inject energy at some very small kf, and then you propagate this front to larger and larger k, and you establish the momentum, the power law momentum distribution in the wake of this momentum distribution, you'll see that this picture is completely consistent with what we observe. And there are some interesting statements to do. I'm not going to go into the detail, but you realize that the particle flux has to adjust to sustain a direct energy cascade, which means that when you have a steady state, the system actually has to find where the dissipation scale is before we can actually get the steady state, because the particle flux decreases when when the time increases, or when UD is larger, while for the energy flux, this is always constant. Okay? So now what is interesting about this particle having to adjust leads to a very simple testable quantitative prediction about the cascade front dynamics, and this is going to be my last slide, which is just to make a very simple argument. So suppose that I consider the energy in the inertial range between some value k naught, that is somewhere in my inertial range, up to a certain value that is the front of the cascade front. And so the energy included there is just the integral of the energy density there. So now when I shake my system, I basically push forward my cascade front just because my system needs to accommodate more and more energy. And so I can just do a very simple balance to see how fast I need to push my cascade front in order to accommodate a given fixed energy rate. So I just write my energy as dE by dt, and just putting together this equation, it's very simple to write down a differential equation for the cascade front. And one of the subtlety here is that I use as an input parameter the actual exponent of the momentum distribution. Now you put all this together and you solve this equation, and you find that the time that it takes for the front to reach a given trap depth UD is going to be a power law of UD, and this power is a very simple function of my exponent. So it means that the momentum distribution k minus gamma has to be consistent with the speed of the cascade front. So when you put that on a graph, we just extract these points here, these threshold points, and we put them as a function of the dissipation scale. And what we find again is that quite nicely over an order of magnitude, the time for the onset of losses scale as a power law, and we can extract the number both from experiment and simulation, and we see an excellent agreement with what we independently measure for the cascade exponent gamma. And just as a final note, it's actually quite nice after putting all these pieces together to realize that when you look at a turbulence in real space, so these are simulation, the problem looks very complicated. You see large structure breaking into smaller structure. Just by looking into Fourier space, then suddenly things become extremely simple. You actually see from numerics how the front propagates and the power law establishes in the wake of the front. And what you can do is rescale these k and n of k to actually show that this is indeed self-similar dynamics. And what we find is that by doing this rescaling a and b that depends on my beta from before, we indeed get something that falls onto a single line. So you see that depending on the point of view, things can look very complicated or very simple. Yes, so, well, I might make a mistake if I tell you on the spot, but basically B is going to be related to the front speed of K. So basically it's K over KCF, right? Exactly. Well, you can do both of them independently. So here, what we did is, we actually put those values for A and B. We didn't try to fit and get the best value of A and B. You can actually do that, and you see that it's consistent. Which one is most accurate is not. I'll tell you after. Yeah. Okay. So let me go to the conclusion. So what I showed you is a consistent picture of a wave turbulent cascade from the energy injection at the larger scale, how we have a direct cascade both of energy and particle, but in a sense that at infinity the particle cascade actually goes to zero and the energy cascade becomes constant. We have a scale invariant propagation of the front. We have a quite convenient way of measuring these these cascade fluxes that are ultra cold atom specific, we have quite a good agreement with no free parameter GPE with a dissipation that is very much like the dissipation we have in experiment in a surprising regime where it wasn't obvious before the fact that it would actually work. And just to sort of dissipate a little bit the idea that we actually understand absolutely everything, that's not exactly true. If you look more carefully, there are various corners that you know, the problem looks like sort of like a Swiss cheese, that there are some pieces that we don't understand very well. We want to have a deeper understanding of what is exponent and why it's not exactly the weak wave turbulent prediction. The detail of the cascade formation, how do you go from nonlinear coupling between discrete modes to actually a continuum propagation in momentum space? What is actually the transition between anisotropic forcing and anisotropic turbulence? This is actually ongoing work at the moment, and whether there is some threshold amplitude effect. Why does GP work so well? Some more interesting higher order statistics that can be done here. Something that's actually related to a talk earlier today, the relaxation dynamic seems to have a very interesting relationship to phase ordering kinetics that we're currently exploring, and it would be nice to have sort of an analog, very simple situation for vortex turbulence. And with this, let me just acknowledge all the people that were involved in various places and various stages of this experiment, and thank you for your attention.